In this video, we're going to analyze a couple more AC circuit problems, and we're going to start with the one that you see on my notepad here, where we're going to find the voltage across this capacitor as a function of time. Now notice in this problem we're given the impedances to begin with, so we don't have to calculate them from the element values. You can see that this capacitor has impedance minus J 6 ohms. All the inductors have impedances of J 9 ohms, and then we got a resistor over here of an impedance of 9 ohms. And then the source voltage here is given as a function of time, and then here's the phasor notation. 36 amplitude at an angle of minus pi over 3. So here the angle is given in radians, and in case you've forgotten, minus pi over 3 radians, right, where pi is equal to 180 degrees, that's the same as minus 60 degrees. Okay, so sometimes the thetas are given in radians, sometimes in degrees, and you just got to know how to convert between the two. And omega, as you can see right here, omega in this problem is 3 radians per second. So one way we could do this problem is to follow the same approach we did in the previous video, where we found the ZEQ for the source, and then once we found the ZEQ for the source by Ohm's law, we could get the current for the source, and then we could see how the current splits up, and then once we have the current through the capacitor, we can use Ohm's law, namely voltage equaling impedance times current, to get the voltage for the capacitor. But I'm going to do a different approach this time, just to be different, show you some various ways of solving problems, where here I'm going to use voltage divider twice to find what the voltage across the capacitor is. Remember that voltage divider in DC circuits, the general form is VR, the voltage across the series resistor, is equal to the voltage across the series combination times a ratio of resistances, where the resistor you want the voltage for is in the numerator, and Req of the series resistors is in the denominator. Well, for AC, you probably can guess from the previous video when we were talking about current divider equation. Well, in AC voltage divider equation, it's the same form. It's just now you're dealing with impedances instead of resistances. So it's still the voltage across series impedances now instead of series resistances, but it's still a ratio where the ratio is the Z that you want the voltage for divided by the ZEQ of the series impedances. Okay, so same form of equation, just you got Z instead of R. So to start off with, I'm gonna reduce this circuit down into a series circuit where we have our source. Okay, 36, and I'll put in the angle now in degrees, minus 60 degrees. Right, that's our voltage, phasor voltage. And then I'm just going to combine this 9 and plus J9 in series, so that's a ZEQ of 9 plus J9. Okay, and then I'm going to come up with the ZEQ. Okay, the ZEQ of these three impedances. So first, from the perspective of the source, these two here are in series. So minus J6 plus J9. Right, that's just adding these two in series. That will give me J3 ohms. Alright, and then these two in series, which has a ZEQ of J3 ohms, is in parallel with J9. So now if I do product over sum, I have J9 times J3 over J12. Okay, so this is going to be minus 27, right, because J squared is minus 1, and then 9 times 3 is 27, so minus 27 over J12, which I can write as J 2.25. Alright, because 27 divided by 12, that's the 2.25. And then when this j comes up top, it changes sign. So it's plus j here, it changes sign when it goes to the numerator, so minus j, but then there's already a minus sign there that makes it plus. So you see j 2.25, that's the impedance for this J9 and minus J6 in series in parallel with that J9. So you see now I can use voltage divider to find the voltage across the J 2.25, I'll call it V1, and then once I have that voltage V1, well that's the voltage not only across this J9 but also across this series combination of J9 and minus J6. So once I have V1, I can use voltage divider a second time to find the voltage across the capacitor. So see, in this problem we're just using voltage divider twice instead of using current divider like we did the previous problem. Although again, a lot of this is personal preference, so there's no reason you couldn't solve it with the current divider technique if you wanted to. But let's go ahead now and proceed and use voltage divider equation to get V1. So V1 would be the source voltage, which is the 36 at an angle of minus 60 degrees. Okay, and then we want the voltage across the J 2.25. And then if you look back here, the ZEQ is going to be the J 2.25 plus this impedance here, the 9 plus J9. So in the denominator we're going to have 9 plus J 11.25. And if you go ahead and work out the numbers. Now what I did is I just turned everything into polar. So in polar form, this 9 plus J 11.25 has magnitude 14.41. And it has an angle of 51.34 degrees. Alright, and then of course this in polar form is just 2.25 and an angle of 90 degrees, right? Because J is magnitude 1 at 90 degrees. So if you just work out the numbers here, you should get a V1 that has magnitude 5.62 and it has an angle of minus 21.34 degrees. Okay, that's our V1. So that's the voltage, as I said earlier, that's the voltage across this J9, and it's also the voltage across this series combination of the J9 and the capacitor with impedance minus J6, right? Because these two in series are in parallel with this J9, and we know voltages are the same in parallel. So I can finish this problem getting VC by doing voltage divider a second time, where I take V1, right, this 5.62 angle minus 21.34 degrees, and I multiply that times minus J6, which is the impedance of the capacitor, and that's the voltage I want. And then in the denominator is going to be the ZEQ of the inductor of J9 and the capacitor of minus J6, which is J3. Okay, so now VC, right, this is minus 2, right, this ratio here comes out minus 2. So minus 2 times 5.62 is minus 11.24. And the angle is still 21.34 degrees. degrees. Now one thing we can do, and this you don't have to do, okay, it's an option, but we can get rid of this minus sign by either adding 180 degrees or subtracting 180 degrees from this angle. So what I did is I subtracted the 180. So I showed this as a positive magnitude, and then I subtracted 180 to make this minus 201.24 degrees, or 34 degrees, sorry. And squeeze in volts here. Alright. That's units of volts. Ran out of room. So you see, that's our answer for capacitor voltage in phasor form. Now we can write it as a function of time by just putting in the source frequency. So as a function of time, Vc of t would just be 11.24 cosine omega is 3, so 3t minus 201.34 degrees volts. Alright, so that's our answer to that problem. Now, let's do one more problem here, and that will finish up AC circuit analysis as a topic, but we'll be doing more AC analysis for the rest of the quarter within the context of other topics. So let's look at this problem. Here's a problem where we just want to find the voltage across this 20 ohm resistor. And we're given the source value. Now, like I said, if not given, I like to write our sinusoidal voltages and or sinusoidal currents depending on the particular problem. I like to write them as phasors. So this 10 cosine 200t, 200 here is the omega. I like to write this as a phasor to start off with. So this is 10 at 45 degrees volts. Now, in this problem, we could, again, attack it from finding ZEQ and then, find the current for the source and see how the current splits up and then get voltage from Ohm's law. But in this problem, I'm going to use voltage divider again. You're going to see it's only going to take one equation to solve for what we're looking at, or what we're looking for, which is the voltage across this 20 ohm resistor. See, remember that just like in a DC circuit, voltages in parallel are the same. So you see, this 10 ohm resistor has the same voltage as the source because the 10 ohm and the source are in parallel. Also, this 20 ohm that's in series with these two in parallel, well, that path has the same source voltage as the 10 ohm because these two in parallel in series with this 20 are in parallel with the 10 and in parallel with the source. So if I just do one reduction, if I just do a ZEQ for this inductor and capacitor in parallel, I'll then have a series circuit of this 20 ohm along with the ZEQ of these two in parallel with a known voltage across them, which is the source voltage, so I'll be able to use voltage divider equation. So you see what I did is I did product over sum with J10 and minus J20. So when you add those up, you get minus J10 on the bottom. Right, so you see you're going to get 200 then minus J squared, which is positive. So this is going to be 200 over minus J10. So you'll get 20. The J comes up top and changes sign. So the ZEQ of that inductor and capacitor in parallel is just going to be J20 ohms. Okay, and now to find the voltage across that 20 ohm resistor, I can use voltage divider because I got a 20 ohm in series with J20 ohms. So the voltage across that 20 ohm resistor will be the source voltage, which is 10 at 45 degrees. And that's times a ratio of impedances where 20 is in the numerator, 20 plus J20 in the denominator. And if you go ahead and work this out, and I think you can see the degrees will come out 0 because 20 plus J20, that's going to have an angle of 45 degrees. And since this 45 degrees is in the denominator and this 45 degrees is in the numerator, and we got something here that's purely real that has 0 degree phase angle, your overall angle for the voltage across the 20 will be 0. And then if you go ahead and do the magnitudes here and do the multiplication and division, you'll see that the voltage across that 20 ohm, it comes out to 7.07 at an angle of 0 degree volts. Okay, that's degrees again. So now the voltage as a function of time across that resistor will just be 7.07 cosine the source frequency, which is 200t, right? And the angle is 0, so we don't show an angle, and that's the answer. Alright, so like I said, these two problems here will finish up AC circuit analysis as a topic, but we're still going to be doing AC analysis like this for the rest of the quarter, just within other topics such as frequency response and AC power.